Okay, so we're now wanting to really solve this differential equation and determine what our Green's function is. So to solve this Green's function equation, there are a few things that I want you to note. So the first thing is that this differential equation that we have to solve is linear. It's a linear differential equation. And what I mean by this is it's linear in G. Okay, so I mean no, sorry, no G squareds or G cubed or anything like that. Okay, so that's the first comment. The second comment that I want to make is the coefficients are all constants. And what I mean by that is, I mean independent of x mu. Okay. And if you ever meet an equation, which is a linear differential equation of this type, so only g's appear, no higher powers of g, and the coefficients are all constant independent of x mu, you should always solve it in exactly the same way. Solve by moving to Fourier space. So let's talk about how you do that. So to move to Fourier space, we're going to use the Fourier representation for the Green's function and for the delta function. So let's write down the Fourier representation for the Green's function first. So the g of x comma y is equal to, we'll have an integral, the 4p over 2 pi to the 4, and then we'll have an e to the I p dot x minus y. Now notice something, okay? This is an important point. I have put in depends on x minus y and not x and y independently. So what I'm using here is translational invariance. I told you that was going to be important, and this is the step where it's important. It's important when we write down this Fourier representation for g of x comma y. And now, let me just write this out completely explicitly because we're going to use this for a moment. So this d4p means we're integrating over all four components of the four momentum, okay? dp2, dp3 over 2 pi to the 4. Oh, sorry, guys. Of course, I need my g of p here. That is the Fourier transform of g of x comma y, okay? And then we'll have an e to the I, we'll have p naught, tx minus ty, then minus I, p dotted into x minus y. And then we've got our function g of p. And finding g of x comma y is equivalent to finding g of p. So that's what we want to determine. What is g of p? And there we have it just written out very explicitly so that we'll be able to use this in a minute. Good. The other thing that we're going to need is the Fourier representation of the delta function. And once again, I think I've said this before, but let me say it again. This is such an important formula, you really should commit it to memory. And the delta function, delta 4x minus y, is an integral d4p over 2 pi to the 4. And then we have e to the I p dot x minus y. Good. Now what we want to do, we want to actually apply our differential operators. We want to rewrite the green box using these two Fourier representations. So let's do that. So what is this green box? So we've got d mu, d by dx mu, d by dx mu. So let's write this out explicitly. Well, there's a d2, dtx2, So we want to differentiate with respect to tx twice. Then we've got minus nabla acting on x, dotted into nabla acting on x. And then we've got m squared. And this operator needs to act on g of x comma y. And this will be equal to delta 4 of x minus y. Good. Okay, so that's just the green box rewritten. So now let's just plug in our Fourier representations. Now notice, okay, let's write this side. So I'm going to use g of x comma y. So I'm going to have an integral d4p over 2 pi to the 4. And then I'm going to let these differential operators act. So if I act with d by dtx, where does d by dtx act? Well, take a look, okay? Look at the piece that I've just underlined in green. If I differentiate that with respect to tx, what do? I bring down an ip naught. So the dtx2 will become ip naught squared minus. When I calculate the derivative with respect to spatial x, I bring down minus I spatial p. So I'll have minus I p dot minus I p. And then we've got plus m squared. And then we'll have e to the I p dot x minus y g of p. So that's the left-hand side of the equation in the green box. Now notice something. I took this differential operator acting on g of x, I took it all into the integral over d4p. Well, I can only do that if the coefficients are all constants independent of x mu. So what I've done here, I use the second assumption that I've got just constants independent of x mu. In fact, okay, good. So let's keep going. So what should this be equal to? Well, this should be equal to the delta function. So let's write down the integral representation of the delta function. This is integral d4p over 2 pi to the 4. And then we've got an integral of e to the ip dot x minus y. Now take a look at this equation. We're equating two Fourier transforms equal to each other. But if two functions are equal to each other, their Fourier transforms are also equal to each other. So what this equation means is, it means I p naught squared, which is minus p naught squared, minus ip dot minus ip, which is plus p dot p, plus m squared acting on g of p. Okay, so that will be equal to 1. And I've just said, what I've said is, if these two functions in this blue box are equal, their Fourier transforms would be equal. And the left-hand side of the equation in the blue box is just the Fourier transform of minus p naught squared plus p dot p plus m squared plus times g of p. And the right-hand side is just the Fourier transform of 1. Good. So that's what we've gotten. Did I already make a mistake? Yeah, sorry. Remember that in quantum field theory, we always put in a minus I on the side of the equation, okay? So I dropped the minus I. Let's see if I can fix this equation a bit better than I've done it here. So this equation, sorry, the starting equation had a typo in it. So the starting equation should have minus I there. That's better. So when I come to solve this equation, I should also have a minus I. So let's put that in. Good. So minus I there. So on this side of the equation, I should have minus I. And over here, I should have minus I. Now notice what's happened. When we started off, So over here, we had to solve a differential equation. When we've gotten to this point over here, we have to solve an algebraic equation. Algebra is always easier than calculus, and that was the advantage of this method. If you have a linear differential equation with constant coefficients and you Fourier transform it, you move to Fourier space, you will always turn your differential equation into an algebraic equation. So that's why we did this logic. By the way, if we had terms like g squared and g cubed, the trouble with those terms is that the Fourier transform of g squared, for example, is a convolution of g of p with itself in momentum space. So when you Fourier transform powers of g, you get non-local integrals in Fourier space. So that's why we had to have just g appearing and no g squared or anything like that. But look how easy it is now to solve this equation. Well, we learn that g of p is just equal to I over p naught squared minus p dot p minus m squared, which can also be written as I over p squared minus m squared. And as usual, by p squared, we mean p mu. Okay, so that's what g of p is. So nice, easy solution. And so now we can write down what is g of x comma y. So let's do that. So g of x comma y is equal to an integral d4p over 2 pi to the 4 I over p squared minus m squared. So great, we've solved our differential equation. Now, there is something that I'd like to prove now. Oh, sorry. What am I doing? We also need the e to the I p dot x minus y. There we are. Good. Okay. And I just took our Fourier representation and plugged in what g of p is. Now that we've got this answer, I want to prove something that I said that we would prove. So let's look at g of y comma x. What is this equal to? Well, this will be an integral d4p over 2 pi to the 4 I over p squared minus m squared e to the I p dot. And now we've swapped y and x around. So we'll have y minus x. Okay. Now I want to make a change of variables. So do a change of variables. I want to take p mu and change it into minus p mu. Okay. So I'm going to be very quick, but I think you know enough to do this in complete detail and convince yourself that I'm not sneaking in anything under the carpet. So this will be an integral. When I change p to minus p, the measure is invariant and the integration domain is invariant. So that doesn't change. I'll have I over, and now p squared is obviously even. So that doesn't change, minus m squared is a constant, doesn't change. And we get e to the minus I p dot y minus x, because we've changed p to minus p. But if we take that minus sign into the exponent, which is trivial manipulation, what do we get? Well, instead of e to the minus I p dot y minus x, we can write this as e to the I p dot x minus y. But look, just above us, this is nothing but the g of x comma y. So what did we just prove? We just proved that the g of y comma x is equal to the g of x comma y. That's something that I said that we would prove. Okay, great. So we have written down a solution to our differential equation, but of course it needs to be improved. Why does it need to be improved? Well, we would like to do this integral over d4p if that's possible. And that's what we're going to turn to next.